Hello everyone. Today I will be talking about another important aspect of vectors which come about as a consequence of the different operations that can be performed on vectors, and this is in terms of velocity. As you have seen, this poses a lot of difficulties when analyzing problems which are related to it, and the topic for today is relative velocity. So as simple as it may sound, relative velocity problems sometimes are very difficult to interpret and get an intuitive feeling of how exactly the problem is posed in the first place. So I'll try to simplify it with the formulation as much as possible, and we will see how the proof is done. So relative velocity, as a definition, we can say that the term relative velocity means the vector differences or the difference between two vectors. If I consider a vector in one dimension that can be a scalar, and the problem reduces by one order, and that is simply basic algebra. But then when we go into higher complexities and higher dimensions, we see that this analysis is highly useful. So for this problem, let us consider two bodies, one moving with the velocity v1 and the other moving with the velocity v2, and let us keep in mind that these velocities are consistent throughout the course material that has been given, and both of them are in a Newtonian frame of references. We do not consider non-inertial motions or anything like that. So we will do a simple analysis of how this is seen in the first place. So when we talk about relative velocity, the word relative means with respect to one another. So if I'm considering v1 as my base velocity and v2 as the velocity that I'm interested in, and I want to calculate the difference between v2 and v1, then I'll give two names to v2 and v1 so that our analysis is simpler when we go to go through the mathematical process. So we consider motion in a two-dimensional system. For one dimension, as I said already, the complexity reduces by one order, which means that you just need to solve a scalar problem. So as you can see over here, for the first case, we say that this body is having a velocity v2. Let's take this direction as our x-axis. So for this direction, we see that v2 has a velocity with starting point O2, and v1 is my velocity. So this is my velocity, or I would sometimes call it a self velocity, and v2 is the other velocity. v2 is the other velocity, which means that I'm interested in figuring out what is the difference between v2 and v1 in terms of relative motion. So let's say v1 is a car which is moving at some particular v1 meters per second, v2 is moving at some v2 meters per second, and I want to calculate what is the relative velocity of v2 with respect to v1. So I have given some steps which might facilitate you to go through the analysis stepwise. So first, check the self velocity, or the velocity which you have, which is also known as the base velocity, or the velocity with which the other velocity is being compared with. So that means that I'm interested in figuring out what is the other velocity with respect to my velocity. And for this example, as I have shown over here, these two things are given. So this is step one. You need to figure out what the two velocities are, the directions that they are in, and since it's one dimension, we need not bother about any other spaces. We just need to be concerned about the linear dimension that we have, and we just need to ensure that these two velocities are in place or clearly defined in the problem. So for step 2, and this is an important step, I would say, consider placing this velocity vector v1, which is this vector, consider placing this velocity vector right on top of this vector, right on top of this vector. So essentially what I'm trying to say is, let's say if this is my v2 and this is my O2, and I'll choose a different color for this game. So I put my v1 right over it. So this is my v1, this is my v2, and I have merged points O1 and O2. That's it, that's what I've done, right? So consider placing vector v1 right on top of v2 so that O1 and O2 coincide. So this is what I've done, and it's pretty simple. We just need to merge O1 and O2, and you can see that this clearly is the case. Now what we need to do is we need to reverse the direction of v1. So let's say if I have, I'll change my colors again. So let's say if I go to O2, this is my V2, this is my O2, and O1 is the same. And then I reverse the direction of V1. I reverse the direction of V1. And that's it. This is all we need to do in order to arrive at a mathematical conclusion. Because now that we have done it, so let's just repeat the steps again. So first identify the vectors in step 1. Then we need to consider placing the velocity vector v1 right on top of v2 and then flip it in step 3. In this process, the physical interpretation of this particular step is that when you do this thing, you ensure that whatever be your velocity in any direction that you have, you flip that velocity vector opposite to it or 180 degrees to it. That's what it means. Either reverse the direction of v1 or rotate it by 180 degrees, and you can use either of them for your understanding. Just flip the vector in the other direction and keep O2 fixed. Don't move O2 because you are interested in figuring out what is the relative velocity of O2 with respect to u. So when I'm saying with respect to u, it means that v2 is subtracted. You subtract v1 essentially with respect to v2, right? So when I'm doing this, I'm basically, and after that, this is essentially algebraic addition. So what I'll do from this step is I just add vectors v2 and v1, and this is what I have, v2 plus of minus v1. I'm not even changing sign. I'm not even doing any other operation. This is basic addition because we are in a linear dimension. We need not bother about any trigonometric artifacts from the thing that we have done so far. And now most of you might have read about this relative velocity formula that is given in standard textbooks, and it is written as v21 is v2 minus v1. I'll just change my color for the time being. So v21 is v2 minus v1. As you can see that this is exactly the same as the one that we did in our analysis. So to get a better understanding of how this happens, of how this formula arrives, I gave you a physical picture of how you can visualize any problem if you are in one dimension with respect to your velocity or the velocity that you're considering for the problem. And this is the magnitude essentially. This is the magnitude which you will get, and the direction, well, if you get a negative sign, it means that you're opposite to your velocity motion, or positive x-axis. So whichever direction you consider as your positive sense. So in that way, you will either have a negative sense, which means that your velocity is bigger than the base velocity, and if it is positive, well, in that case, the other velocity is bigger than you. The other velocity is bigger than you, right? So this is a simple analysis, a simple way to understand how you can visualize velocity vectors and the relative velocity which comes about as a consequence to analyze two different velocity vectors, in fact 3 different velocity vectors if you're going into complex problems, but then this is the first step in one dimensions. So now I'll give you some time to think how we are considering this thing. If we go to a 2-dimensional space, understand that in 2-dimensional space vector algebra works, right? In 2-dimensional space vector algebra works in its full capacity. So the way we would argue at this point that this is not exactly similar to the one which we have done in just before this one is that instead of doing vector algebra, instead of treating them as ideal vectors, we can do a component decomposition the way that I taught in the last module, that means in chapter 1. So the way that this is addressed, what we can do is we can approach the same problem using vector decomposition, or what I would say is if you can resolve the vector into scalars and then perform the exact same operations in both the axes, in that case this is pretty much the same. This is essentially the same problem. right? So in 2D, now we go into the 2D case. So we repeat the same steps, and then one might need to resolve the vector into components as it is in a 2D setting. So as I suggested that we can do the same problem. It's just that you need to decompose it into x and y components and then do the same thing altogether. So for the analysis, let us look at this figure very closely. We see that v1 is a vector, which is the self vector. This is the vector which I'm considering as the base, and I will be calculating the relative velocity vector with respect to it, which means that, let's say if I have another velocity vector, I'll calculate the relative velocity vector with respect to the self vector, which is given as v2 minus v1, as you see over here. And this is the this is essentially not the resultant, I would say, but this is a way by which you can visualize what is the direction, how is v2 changing with respect to v1, and that I feel is the correct word to describe how v2 changes with respect to v1. In fact, what is the difference of v2 with respect to v1? But then this can be equally simplified if we do a vector subtraction. So similar to the previous problem, we have v1 as the self velocity. As I already told you, for step 1, you need to identify the two velocity vectors, and that's a very important artifact, because if you are not given that, there is no concept of relative. The word relative itself compares two things, right? So v2 is the other velocity, which means that this is the velocity which I'm interested in, right? Step 2, and it's a bit different from the previous problem, I just don't put one on top of one another. So given this problem, I have already made sure that this is already on top of one another. If it is not, it's still not an issue, because you can always shift and translate vectors without changing their identity. The direction will still be the same. So yes, I want to focus a bit on this translation. So let's say if you have a vector v in a particular direction, and you simply translate that vector into the other direction, its position vector definitely changes. Its position vector changes, its origin changes, but then its direction, sense, the angle which it makes with the horizontal, so long as your coordinate system is kept fixed, the angle does not change, and its magnitude doesn't change. So if you translate this vector, so let's say if this original vector v1 was not originally placed at O, which I am marking over here. So if it wasn't at O, you could have easily translated the vector so that the tip of the vector is at O, and that would still haven't made any change to the overall analysis of the problem, right? So now I would use some trigonometry and then resolve v1 into two components. One is v1x, which is this component. Choose a different color for that, and this is vx, and this is vy. But now this is for the self vector, so I give another subscript which is v1x, and this is v1y, right? Similarly, v2 is resolved into v2x, and this is v2y, right? So in this way we have resolved the components into two individual axes. And now you can see that this problem is fairly simple now, because for this problem, let's just forget the fact that I have a y-axis altogether. Let's consider I just have the x-axis, and in the x-axis I have two vectors, which is v2x and v1x. That's exactly what we dealt with when we were doing the scalar problem, right? So for the x-axis, we have two components of two different vectors, and we do a v2x minus v1x from the formula that we established in this part, right? Which we established in this part, and this is very fundamental, because we generalized it to the fact that this can be used when we are present in a linear dimension, right? So it's v2x minus v1x, and in trigonometrical terms, the way we have decomposed the problem, it's v2 cos beta and v1 cosine alpha. Similarly, for the y-axis, we have v2 with respect to 1, and this is for the y direction. And once again, I need to emphasize, I'll emphasize what is the importance of considering an orthogonal system of coordinates for the problem. It really simplifies our understanding to make sure that one direction does not interfere with the other, right? So one of the direction is x, and that is what we did in the previous step, and now we will do y, and we can see that there is really no dependence of x on y. So it's orthogonal to each other, and that reduces the complexity of the coordinate system immensely, right? So let's be grateful to the fact that orthogonal system has come into use in modern day physics for almost every aspect, and that kind of really gives a better understanding of how vectors are dealt with, though it's not the same for all coordinate systems, but then a Cartesian or an orthogonal coordinate system really simplifies the problem per se. Right. Again, so for the y-axis, we have v2y minus v1y, and we have the components v2 sine beta and v1 sine alpha, right? And after this point, I think everything is pretty trivial, because we know that, let's say, if we have the vectors v1 is equal to v1x I cap plus v1y j cap, and v2 as v2x I cap plus v2y j cap, and this is basic decomposition of vectors into a Cartesian coordinate system, where we have v1x and v2x as the two x components of vectors v1 and v2, and v1y and v2y as the y components of the vectors v1 and v2 respectively, right? And then we do a difference. So we see that because it's an orthogonal system, the I caps and the I caps cancel out, and the j caps and the j caps sort of they agree with each other, and their subtraction is linear. So addition and subtraction on individual axes are scalar operations, which means that v2x minus v1x is, again, you take the magnitudes, you just subtract them, and that's it. And again, v2y minus v1y, that's again the same thing. So it won't count in this case because you have considered the problem in general. Again, you don't need to worry about signs in that case, because when we have constructed the vector, we have taken care of the sign. We did not say anything about the signs, which means that it is an absolute system, which means that, let's say, if you have constructed a vector in a certain way, the components itself will be equal to v1x and v1y, irrespective of the fact that it is plus or minus. The formula will still be valid. You don't need to worry about if the components have positive or negative values. If you use this formula, you can exactly get the values that you are looking forward to. And of course, the direction sense is very important when you are starting the problem, so that you don't end up with different values for the end, because the direction sense is very important when you're considering. For example, if you see my diagram, I have mentioned that this is my positive x, this is my negative x, this is my positive y, and I did not give a negative y because I know that for this problem you don't have a y component in the negative direction, but I highly suggest that for every problem you should have a negative y as well, so that if you get any component along the direction, it really helps to decompose it, as it is pretty trivial. So now we sort of write it down and see what is the final expression. Let's see. So it's v2 cos beta minus v1 cos beta I cap plus v2 sine beta minus v1 sine alpha. Oh, I think I got something wrong. Maybe this is wrong. Yeah. So this is alpha. Nothing. So this is nothing. Okay. Sorry about that. So v2 sine beta minus v1 sine alpha j cap, right? So this is the final form of the velocity vector. This is the v relative, let's say v relative x component I cap plus v relative y component j cap, where v relative is equal to v2 1, right? So this is the final form of the v21 vector. This is the relative vector between v2 and v1 when v2 is compared with respect to v1, or you can frame it as if v2 is subtracted from with respect to v1, or v1 is subtracted from v2 in terms of vector setting. And relative velocity is a topic which really makes you understand what is the implication of vector addition and subtraction, and how does that follow. For example, if these two vectors were in a three-dimensional space, the analysis would have been exactly the same. It's just that you would have needed to decompose the vector into three components instead of two, and then the analysis is the same. You first take the vectors, make sure that they have the same origin, and then you decompose them into components, and then consider each direction, and then take the differences between the vectors in that particular direction and calculate the relative velocity of one with respect to the other. Right. So once this is done, and we know that VR is equal to V21, then we calculate the magnitude of the relative velocity, and for this problem, since we know what is the value of v2x minus v1x, so this gives you the magnitude, and this is essentially some calculation from your end, but it won't be very difficult. Cos squared alpha, did I do it right? Yes. And then v2 sine beta minus v1 sine alpha square, and this would require some calculation. As you can see that this will require some hard work to do it, but I think we can probably go ahead and just see what's in store. And cos beta plus v1 cos square alpha plus v2 square sine square beta is 2 v1 v2 sine alpha sine beta plus v1 square sine square alpha. So as you can see that this is an identity which follows, taking a different color again. So this turns to 1, this turns to 1, and this thing will remain in the expression for some time. But then this is exactly the magnitude of the relative velocity vector that you can see over here, right? I'll leave it to you as a final exercise to reduce it to a trigonometric identity as much as possible. So this won't be very difficult an exercise for you as well, because you can see clearly that if you take 2v1 v2 as common, you get a cos alpha cos beta plus sine alpha sine beta, and then the rest of it is pretty simple, right? So, and it's basically cos alpha minus beta, so it won't be a problem for you to understand. So yeah, and now the direction of the relative velocity vector, if you have tan theta is equal to v2y minus v1y, and you just essentially plug in the expression from the above. That's all you need to do. And sine alpha divided by v2 cos beta minus v1 cos alpha, right? So this is the expression, and this is pretty trivial. If you know the values of alpha and beta, and if you know what is v1 and v2, I think that's pretty much what you need to consider for the problem, and that is pretty much it. But then oh, I think I missed out something. Maybe what I can do is let's just see. Okay. No, I think it's fine. Yeah. So I should also mention. Yeah. So I should also mention how you get this angles alpha and beta. So how do you get alpha and beta? So for some problems, what we have is when you do your problems from the book, you will see that many of the problems are given in terms of a ship is moving 20 units north, 50 units west, east, 50 units east, and that will give you a sense of where the velocity vector is. And from tan theta, so let's say if this is your vector and you have moved some units up north and some units up east, let's say you have moved 4 units east and 3 units north, so tan theta is given as 3 by 4, right? It's pretty easy. And theta equals to tan inverse of 3 by 4. And from there you can get the value of theta. So alpha and beta may not always be given directly. It may be given in this form or in some other form which needs to be calculated first. And that won't be a very difficult exercise because that might require some basic trigonometry and maybe some algebra to find out what is the value of theta, maybe Lami's theorem, which I taught you in the last class. So from this way onwards, you can calculate what is the relative velocity of that vector and then begin to solve higher problems. So this is the end of the special module, which was relative velocity. I would appreciate your suggestions, and until next time.